Hi, everybody. My name is Guilin Li. I'm a PhD student at Huazhou University of Science and Technology. Now, I will introduce the progress of the investigation for thermal gradient effect in space gravitational wave detection mission, TianQin. The content of my report include 5 main points listed as follows. TianQin is a proposal for space-borne detector of gravitational waves in millihertz frequencies. The ultra-high precision inertial sensor is a key technology in this mission. Thermal fluctuation noise should less than 0.52 times 10 to the power of minus 50 meter per second square per root hertz and 6 millihertz. But we can see there is a drift. This value is related to the activation temperature and outgassing effect. The temperature gradient effect includes radiation pressure effect, radiometer effect, and asymmetric outgassing. Radiation pressure is exerted by electromagnetic radiation from the surfaces inside the electrical housing and test mass system. For radiometer effect, molecules coming from higher temperature zones transfer more momentum than molecules come from lower temperature zones, producing a force on the test mass. Any surface exposed to an atmosphere at a given pressure presents an interchange of particles with the environment. Asymmetric distributions of the outgassing rates and the inner surface induce different pressure distributions that can lead to net force over the test mass. In space, the temperature gradient effect is mainly displayed on both sides of the test mass sensitive axis. It produces a translational motion force. However, there is no microgravity environment on the ground, so we adopt the torsion pendulum device. We measure the torque generated by the temperature gradient effect by measuring the angle, and then we can use the equation of motion transform it into force. This is a schematic diagram of the torsion pendulum device. The hollow test mass is suspended by coarse fiber. The mirror can reflect the rotation angle of the test mass, and we measure this by the autocollimator. The heater and temperature sensor are pasted on the outside of the electrode. The heater can produce periodic temperature fields, and the torsion pendulum is suspected periodic motion, as shown in the formula. Under the modulated temperature field, the torque subjected to the torsion pendulum mainly includes two parts. N0 is torque of the torsion pendulum without the temperature modulation, and the first term is the torque exerted by the temperature modulation. By digital demodulation and low-pass filter, we can extract the torque exerted by the temperature field N delta T. We can see that only the radiometer effect related to pressure, so we can measure N delta T at different pressure. And we can fit it linearly so that the slope is this term and intercept is this term. So we can effectively measure the radiometer effect. The radiation pressure can be calculated by simulation, so the outgassing effect can also be obtained. The signal stage torsion pendulum is placed in a high vacuum system. This is a test mass and electrode housing. This picture shows a sensitive probe after it has been assembled. The table gives the specific parameters of the torsion pendulum. We use a small valve negative temperature coefficient semester as a heater and temperature sensor probes. It is mounted on the back of the electrode, not on the back of plate. This installation can effectively restrain the edge effect and shearing force effect. It's worth noting that area A should take areas of two plates of the x-axis. The table shows the parameters of heaters for heating modulation. Here is the semester and temperature measurement circuit. I'm going to show some of our results. The first diagram shows the periodic temperature field generated by the heater. The second picture shows the angle value of the torsion pendulum measured by the autocollimator. The last picture shows the torque effect of the torsion pendulum obtained after data processing, and the response is caused by the temperature difference. We also need to modulate the pressure. This is our pressure modulation range. The pressure is maintained by the molecular pump. Is measured using an extractor measurement system. The pressure change achieved by changing the opening and closing size of the gate valve. This graph shows the pressure measurement curve for 3 consecutive days. We can see that it has a good degree of repetition. By modulating temperature and pressure, we end up with this picture. This term is slope of fitting curve, and this term is the intercept. And then we have these quantities down here. The acceleration noise of TianQin inertial sensor can be expressed by the formula. Under these parameters, the total noise contributed by the temperature gradient effect is 8 times 10 to the power of minus 17. This is the upper limit of the temperature gradient effect in TianQin inertial sensor based on the experiments. Meanwhile, through TianQin's noise allocation, we can calculate that the maximum temperature fluctuation allowed is this value. Thermal gradient effect is one of the key noise for inertial sensor in TianQin mission. We have used the torsion pendulum for ground test thermal gradient effect and got the upper limit of thermal gradient effect. We will investigate the thermal gradient effect on the variety of thermal gradients, ambient temperatures, and pressures. We will further study and control the outgassing effect by changing the plate with different materials and baking under different conditions. Thank you for your attention.